here? Well, this is called master-master replication. And based only on the picture, what problems does this solve? And what problems remain?
You can have multiple masters, so you no longer have the problem of the one master getting too full.
OK, good. So you have multiple masters, so you no longer have the obvious problem of just one master being full. You no longer have a single point of failure. You have 2 points of failure, but at least probabilistically, that they're both going to die, you would hope, at the same time, is at least a little less likely than just one of them dying. So that seems a plus. But what problems remain? So there's still some latency. So the arrows from left to right and right to left suggest that in addition to replication from master to slave, master-master replication is also happening here. So in this kind of model, you might very well have another device in the picture, like a load balancer, that decides either via round robin or via load to send inserts and deletes and updates to this guy or to this guy, or maybe always to this guy, but the other guy is always getting copies of them so that he can be promoted if one of them dies. But in short, you introduce some more robustness here, more reliability, but there's also a cost, quite literally financial, right? So it's very easy to just say, well, if we have single points of failure, let's solve the problem by doubling the amount of hardware we have, but this literally has non-trivial implications. As an aside, and as you kind of think about what you might want to do longer term if running your own site, Amazon also has an elastic database service whereby you can create a MySQL topology and have it scale laterally with replication even just by running some commands or clicking some buttons on their website. So you don't need, even though we've drawn things here as pictures, as from this book excerpt, you don't need actual physical hardware. So now let's paint a more complex picture, which is perhaps a little more representative. So at the top, we have some client network like the internet. We have the load balancer. We have a whole bunch, 5 of web servers. The arrows then are pointing downward. Let me zoom in if the text is a little small. The arrows are then pointing apparently to a load balancer on the left that then dispatches across MySQL slaves. And then we have one master server on the right that is replicating in turn to the slaves down below. So it's getting complicated, frankly. So it's getting expensive, but we're starting to now combine some of these ideas. But there's still some, there's still some problems here. Find fault with this topology. Yeah, Zach.
Still all the requests are coming to one load balancer.
Yeah.
Right?
It doesn't matter how fancy your internal architecture is, how pretty your network topology picture is, no matter how impressed your boss is, you're still an idiot if you still have, despite all of this effort, a single point of failure that could have been avoided. Now, in fairness, maybe it's a financial decision, and maybe what you do in this case, because this is all you can pull off financially, is maybe you invest in a very expensive load balancer for the very top of the picture, or at least a very expensive support contract, so that if it does go down, the company will replace it within 4 hours, literally on site. So this kind of mitigation is possible. But if you're just doing it and then crossing your fingers, not the best idea. So what would be an obvious refinement here? OK, yeah. I mean, sometimes it's as simple as that, like multiple load balancers. And indeed, what you can do then is have 2 load balancers that dispatch across those 5 servers. But now we're adding a complication. If we've got 2 load balancers, what's the implication for DNS and for the IP address and all of this? How do I decide which load balancer to send traffic to? RJ?
You could add a load balancer to the load balancer.
You could have a load balancer to the load balancer, and this seems to be kind of a vicious cycle, right? Because then we have a new single point of failure, so we need a second load balancer, but now we have to balance load across these 2. So hopefully there's a solution here. And indeed there is. So there's network level tricks that you can do whereby we could introduce to this picture 2 load balancers side by side, but that have only one IP address. And what you do is configure the 2 servers in such a way that they are highly available. HA is the buzzword here. And what they do is they send heartbeats to one another, which is essentially like a ping from left to right and right to left. And what happens is as soon as one of those servers does not hear the heartbeat from the other. It assumes that he is down, and what the remaining server does is take control of that IP address at a network level. And this is done, if you're familiar, if you took 143, ARP is involved here, ARP, Address Resolution Protocol. The server gets involved and then says, I shall be henceforth IP 1.2.3.4 until this guy is brought back online, and then maybe you can have the IP address back. So you have one IP, but it floats across two servers, and they decide dynamically whether or not the other guy is alive. Now, of course, problems here could happen too. Find fault with this story. What else could die in this story, even if it's not pictured on the image?
The network between the two.
Perfect, right? What are these two load balancers connected to? Well, probably a switch, like something bigger and more expensive than the switch or the home router you have at home, but two Ethernet ports. Now, if those two Ethernet ports are in the same device, you're still an idiot, right? Because you've just now moved the single point of failure from server level to network layer, but this too is bad. So typically in this picture, we would scroll up even higher, and we would actually have two switches in the picture. And you would actually connect this load balancer to this switch, and to this switch with two Ethernet cables, and then this guy would be connected conversely to both of them across both switches. So you really have this mesh effect. And even though this is getting increasingly complicated, these are actually robust engineering solutions to this. But this is why, frankly, services like Amazon's are so increasingly compelling, because, my God, like, even as your eyes start to glaze over with all of this complexity, it is complex, and it's hard to get right, and it's expensive, and you need someone 24/7 on site, perhaps, to actually make sure to respond to all of these things. So a lot of what you get in the so-called cloud is the virtualization of these services. You get the illusion of multiple switches, but there are actually multiple physical switches. You just don't need to know about the actual wirings thereof. But this really is a theme, right? As soon as you see a single point of failure, it's an opportunity to actually improve there. And this picture, too, doesn't need to be taken literally. We don't necessarily need to buy a new load balancer just to do database replication, database load balancing. It can be the same device, just operating on a different TCP or UDP ports. But this theme of doubling resources is actually quite common in approach. Yeah?
So the MySQL, like the MySQL database, can it store like images or other types of data?
Good question. Can a MySQL database store images and other types of binary data? Yes. You can store them in blob fields, binary large objects. Typically, this is one of these religious things. I would typically say you shouldn't store images in the database, since they're really meant to be storing data, whereas a file system has been optimized over the years for files. And so indeed what you would probably should do is store the paths of files or the file names of files in your database, but then store on disk somewhere on an actual web server or something called a CDN, Content Delivery Network, the actual files. Like Akamai is one, and Facebook has its own now. That just stores static content.
So where would that be in the picture?
So it could be, so for the CDN type services. So if you were hosting it yourself, the CDN would live at the web layer, which is those 5 servers up top there. They're just web servers. But typically CDNs are so intellectually uninteresting that they're typically outsourced to people like LimeWire, one of the two. One of them is P2P, peer-to-peer. Or Akamai or some other services. Amazon has their own as well. And you just get some unique long path. In fact, if you go to Facebook, frankly, later today, pull up any friend's photo, right-click on it, choose copy link location, and then paste it into your browser bar, you'll probably see that it's fbkn.cdn or something like that. It's stored on Facebook CDNs, some of which might be outsourced. All right, how about this one? So partitioning is also a solution, and it actually might be more reasonable, especially since you might think that the previous picture is like many years away from being your problem, perhaps. So what about partitioning, though? Right? And if you were on Facebook very early on, so like in the mid-2000s, what was the URL of what were the URLs of Facebook's Facebook? It wasn't always www.facebook.com, and it wasn't always www.thefacebook.com. Yeah, so back when it first started, it was harvard.thefacebook.com and mit.thefacebook.com and bu.thefacebook.com. And this is when Mark and company were initially scaling things up, and relatively quickly did one single server not prove sufficient. So what's the quickest overnight change that you can make to scale a website, to roll out some additional school or handle more load? Well, if you had one server originally, right? Go to 2 servers, right? And make one called harvard.thefacebook.com and another mit.thefacebook.com. Duplicate the database schema on both, duplicate the code on both, and then just use DNS to actually route users to the right one based on, or just tell them, go to harvard.thefacebook.com or mit.thefacebook.com, have them select from a drop-down menu, or based on their login, based on their email address, just redirect them to the appropriate server. And I'm probably oversimplifying the original story, but early on, they did use partitioning. So what does partitioning mean? It means sending some of your users here, some of your other users here, or more generally, putting some data on this server and some data on another server, partitioning it logically based on some rule of thumb. And the rule of thumb in Facebook's early days was if you were a Harvard affiliate, you went on this one. If you were MIT, you went on this one, and so forth. So a picture might look like this. On the left-hand side, you might have a load balancer that sends load across multiple SQL servers, but only for people whose names start with A through M, for instance. And on the right side,